Um,
I only work for the local tech. What I'm saying,
ouais, dans ce moment, il est marié.
I'm not going to steal more of Richard's time telling you that he's from UC Irvine and are you a linguist or a psychologist or a computer scientist?
Department of Language Science.
Language science, so that covers all of it. And the rest will be told to you by Richard. Go ahead, welcome.
Great, thanks. So it's a real honor to be here, so let's get to it. So I'm going to start with an idea from neuroscience. So this guy, David Marr, wrote this book called Vision, in which he is trying to figure out the general principles of how it is that you can take in data from your eyes and pass it through a bunch of neurons in your brain and make sense of your visual data. And he ended up enunciating a very important principle for understanding complex adaptive systems. So he says, trying to understand perception by understanding only neurons is like trying to understand bird flight by studying only feathers. It simply cannot be done. In order to understand bird flight, we have to understand aerodynamics. Only then do the structure of the feathers and the shapes of birds' wings make sense. So in order to understand a complex system like this, you have to understand its function, the problem it's solving, and the constraints it's under. So if you want to understand these things like bird wings and their feathers and all the different variety of bird wings you get, if you're an ornithologist, you need to understand aerodynamics because that is the theory of the constraints that these bird wings are under. They have to be able to fly. The same aerodynamic theory that you would use to understand airplane wings. So when you're thinking at this level of function and constraints, we see that you end up using the same kind of theory to understand a natural system like wings and an artificial system like airplane wings. And I think something true is similar for language, for human language, as we are using it and processing it now, and language models as produced and learned by artificial neural networks. So this is true, a good principle for understanding how wings work, for understanding how vision works, and for understanding how language works. So what is natural language? How should we understand what is language from this sort of functional perspective? Natural language is fundamentally a code that enables this kind of communication among humans. So there's an agent A that's like me right now who speaks. There's an agent B that's like you right now who's comprehending. And you could use the same language to speak back to me. So I'm using the English language now. That's a code that enables this kind of communication. And the constraint on the system is that the agents are humans. So I have to be able to speak in real time. You have to be able to comprehend in real time. And both of us have to be able to learn how to use this language, typically while we are children. So let's think about this from the usual information theory picture of communication. So this is the usual diagram that's used in information theory for the basic analysis of a communication system. The first thing that has to happen in communication is that you start with a message or an intent or a meaning that you want to convey to someone or something, and you have to turn it into a signal. In psycholinguistics, we would say that that is language production. How do you start with a meaning, an intent in your brain and turn it into an utterance? You then put that utterance out into the world by speaking. It goes to a comprehender who receives the signal and decodes it back into a meaning. And there are extremely non-trivial information processing constraints that are going to happen at both of these points. That is because
Can I steal my computer? Are you using it?
take it.
Thank you.
So there's very, very non-trivial information processing constraints happening at both of these points because this all has to happen in real time. So natural language as a system was originally only for real-time communication. The asynchronous things we have now, like reading and writing, came much, much, much after the evolution of language as a thing. So the basic function of language is for real-time communication, the encoding step, the decoding step, this all has to happen in real time. It has to happen incrementally. And you have to learn the whole thing pretty quickly while you are a child. So these are 3 points of constraint on natural language: comprehension, production, learning, processing, and learning. Just to give you a sense of like the level of constraint on language, let's just think about what goes on when you describe a meaning like that one. when you describe that as a cat. What you've done is you've taken a meaning which is actually really information rich. So there's 100 million bits of information in just this image. This is just based on the file size of this image. It's this incredibly information rich thing. And when you describe that as a cat, you have compressed that into a signal, which has, how much information do you think is in there? Turns out it's only 7 bits. This is an incredible feat of lossy compression. So there's almost no actual information that's conveyed in language relative to the amount of information in the kinds of meanings we might want to express relative to the amount of information in like our sensory input. So think about everything we can accomplish as humans by coordinating using language. We're able to accomplish that using this extremely low bit rate code. So you are able to look at this 100 million bit source and you're able to figure out what are the 7 most important bits that I need to express about this. It's a really impressive computational feat. This is the level of constraint we're thinking about under which human language operates. But how do I know actually that that's 7 bits? We measure that using information theory concepts. So information theory tells us that information is surprise. When something is more surprising, it conveys more information. So the actual formula that you use is that the surprisal for an event, like the event of encountering the string a cat, is the negative log probability of the event. So that's going to be high. Surprisal will be high for low probability events. Surprisal will be high for low probability events when they're surprising. Surprisal will be low for high probability events. And how did I estimate that probability for a cat? I got it out of a large language model. I got it out of GPT-2, which is a older, dumber ancestor of our modern friends like ChatGPT. So the topic for the summer school for the talk today is about language and language models. And how do we use language models? How do language models fit into our picture of how language works? And we've already seen a little bit of that. So I was using language models to estimate information content, part of a basic information theoretic analysis of language. But this talk's going to be going deeper. And so I need to clarify what exactly I mean by a language model. I think we're going to see that many of the speakers today are going to define a language model differently. People are probably going to mean slightly different things when they're talking about language models. Here's what I mean. I don't mean this is the only definition. This is just what I mean during the following 30 minutes when I'm talking about this. So a language model is any predictive probability distribution on words or tokens given previous words or tokens. So it's a probability distribution on something like a token like cat, given a context like I saw a blah, 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 the previous tokens. And the model's behavior is defined by a lot of parameters. And if you have many, many parameters there, we say it's a large language model. How do you get those parameters? You get the parameters by solving an optimization problem that looks like this. You choose your parameters in order to minimize a loss function. That loss function is the average surprisal of tokens given previous tokens, the same information theoretic thing that we saw earlier. And the bracket and the text thing there is showing that this is an average that you're computing over a very large body of text. What this means effectively is that you're just training your model to maximize the likelihood of tokens, incrementally predicting a token given previous tokens. In addition to that, our modern systems like ChatGPT and its friends have some additional training through things like reinforcement learning with human feedback in order to do something like align. Yeah. So there's some additional training to align the output of the model to some reward model. I'm not going to have much to say about that today. I'd love to talk about it in discussions. I have many thoughts about it, but it's not part of my planned presentation. When I'm talking about language models today, I really mean just these predicted distributions trained on text. Furthermore, today, I'm not so interested in the architecture of the language model. When I'm talking about language models, what I'm interested in is sort of any powerful parametric probability distribution that's doing this kind of prediction of tokens given previous tokens. You're going to hear tons about different architectures coming up, digging into the black box of what's going on inside of the models. What I'm interested in is these things as just probability distributions for now. And that's because, there's a lot of recent work on new architectures. I wouldn't be surprised if transformers get supplanted with some new architecture soon. And so I think the details of the architecture are not as important here. So the two high-level points that I want to argue for today is that using language models, these distributions, to capture linguistic probability distributions, we can model quantitative data about language in multiple domains. It gives us the best probability models for understanding language in multiple domains. Furthermore, we're going to see that the information processing constraints, which are to some extent shared between humans and language models like this, can actually explain properties of human language, why human language is the way it is. We're basically going to see that this kind of predictive distribution plays an important role in understanding language at multiple levels. So here's what we're going to do. First, we're going to talk about what language models learn. Then we're going to think about what they tell us about how humans process language, and then what they tell us about why language is the way it is. So first, what do they learn? Language models are our best probability models for language. They're not perfect, but they're the best thing we have for the use in the various sciences of language. So they provide our best estimates for the probability of a word, sentence, or whole text, and we'll see some applications of that soon. And though imperfectly, they capture many rich and subtle things in language, including world knowledge, style, and the formal grammatical structures that underlie language. So why have I bolded the formal grammatical structures? It turns out that this question of grammatical structure has been a core preoccupation in the science of language for a long time. So I think the first important thing that was said about the relationship between language models and the structure of language was from Noam Chomsky in 1957. He invites us to consider two sentences. Colorless green ideas sleep furiously, and furiously sleep ideas green colorless. So who's seen these before? Many, but not all. So of these two sentences, which one is like grammatical in English? So give me a 1 if you think it's 1. Give me a 2 if you think number 2 is grammatical in English. No one. So the point is that the first sentence is clearly like part of the English language. It follows the rules of English grammar. It has structure conforming to the rules of the English language. The second thing is just like a random word jumble, right? It's like I just opened up a dictionary and picked out random words, and there's no structure to it. It has no grammatical structure. And what Chomsky points out here is that if you just look at language model probabilities, it's probably not going to distinguish the grammatical thing from the ungrammatical thing. So he says in particular, it's fair to assume that neither sentence 1 nor 2, nor indeed any part of these sentences has ever occurred in an English discourse. Hence, in any statistical model for grammaticalness, these sentences will be ruled out on identical grounds as equally remote from English. So the point is that if you just look at probabilities, it's not going to distinguish the thing with structure from the thing that doesn't have structure. We can actually test this idea now. So we can just pass these sentences into a strong language model like GPT-2. Things like this were not available in 1957. I've used this red star here to indicate that the second sentence there is not a real sentence. It's just an ungrammatical string. So we pass these into GPT-2. We can calculate surprisal values. And we actually get that the grammatical, oh, by the way, I'm not actually just going to give it these sentences. These are famous sentences. They're absolutely in the training data for any language model nowadays. And so I'm using a little variant of these sentences to actually evaluate these probabilities. So you actually get that the grammatical thing is higher probability, lower surprisal than the ungrammatical. So does this mean Chomsky is wrong? Does this mean that we can actually just use language model probabilities and identify language structure with language model probabilities? No, his general point I think is actually correct. It's just that this example was bad. So it's not generally the case that the probability for some grammatical sentence should be greater than the probability for any random ungrammatical string. So the general point here is actually correct. And here's an example that does work with modern models that we came up with. Here's an ungrammatical string. Snails died the old. No idea what this means. This is just a word jumble. Here's another sentence. The ancient crustaceans expired. So this is clearly grammatical in English. This has grammatical structure in English, but it is the words are all somewhat odd. So actually each word in this grammatical sentence is like a low frequency variant of a word in the ungrammatical sentence on top. See? So if you pass these in a GPT-2 or really any modern language model, you get surprisals like this. The ungrammatical thing is actually lower surprisal, higher probability than the grammatical thing. So it's not the case that grammaticality, the grammatical structure of a language just is the probability of the string. And I think this is not because the models are making a mistake. I think the ungrammatical thing there actually is a higher probability string than the grammatical thing. Because the grammatical thing with the ancient crustaceans, that has a bunch of weird low frequency words. You're not likely to find that in a text because the words are low frequency. Whereas the snails died the old thing, like, if there's editing errors in a text, you might very well find that string, right? So I think the language models are not wrong here. The ungrammatical thing actually is higher probability than the grammatical. So given that this is how the world works, how could you look at a language model, look at its probabilities, look at the things it outputs? How could you figure out if it has learned the grammatical structures of the languages that it is dealing with? You have to consider that probability is a function of many different things. So one of the things that influences the probability of a string is the grammatical rules of the English language. Another thing that influences the probability of a string is how plausible the meaning is. So this is like an implausible meaning, and so it's unlikely that you're going to encounter that string. Another thing that influences the probability of a string is performance constraints. So this means that there might be some sentences that are just so long and complicated that no human could ever produce them, given our limited brains. And so those are going to be low probability sentences. There's all of these different factors that influence probability for a sentence. By the way, these factors all also influence basically anything that you could measure in terms of human behavior around a sentence. If you're looking at reaction times on a sentence, or acceptability ratings for a sentence, or comprehension accuracy on a sentence, all of these things are going to be influenced by all of these factors and other factors as well. So then how could you look at any of these dependent variables, language model probabilities or human reading times or human acceptability ratings? How could you infer that a system has knowledge of grammatical rules of English? How could you look at reading times and get evidence that humans have knowledge of grammatical rules? How could you look at language model probabilities to figure out that language models have knowledge of grammatical rules? You have to be careful. The key is to come up with sets of sentences of stimuli that are going to control for all of those confounding factors. So here's the kind of study you can do. You can take an ungrammatical sentence like this. The key to the cabinets are rusty. This is ungrammatical because the verb is wrong, right? So the verb should be is. The verb needs to agree with the subject of the sentence, which is key. So this is an ungrammatical string of English. Compare that to a grammatical variant, like the keys to the cabinets are rusty. So you have to think about comparing the two strings. There's actually a non-trivial formal structure that is lurking behind these strings. The thing is that what makes this interesting is that to figure out the right form for the verb there, you have to look back to the subject of the sentence. You can't just look back to the previous noun. You have to find the subject of the sentence. And that's actually a non-trivial thing to do formally. You have to parse the sentence basically. So how could you tell? If you were looking at reading times per word, or if you're looking at surprisal values coming out of a language model, how could you tell if there is an underlying knowledge of that grammatical dependency, of that grammatical structure? You would have to compare reading times or surprisal values for controlled parts of the string. So you would look at the surprisal values only for the R rusty part of the string. That way you're looking at the same words in both cases. You're controlling for all that stuff about lexical items for what words you're using. You can then compute something went missing there. You could then compute a surprisal difference. So here I just passed these strings into GPT-2. I got the difference in surprisal for the grammatical thing minus the grammatical thing. You get a surprisal difference of 1.7 bits here, indicating that the model is more surprised in the first case than the second in this very controlled part of the string. And this is one piece of evidence toward the idea that language models are aware that the right way to form the right way to figure out the form of the verb is to find the subject of the sentence. Of course, what's one example doesn't tell you much. You have to look at many different examples. You have to look at many different variations of the structure. And that has been done. So this is now like a whole subfield in computational linguistics called targeted syntactic evaluation. If you want to like learn more about this, then this would be the keyword to look for the last 8 years or so, I think. Many people, including myself, have been basically coming up with these very controlled tests that you can run language models through. Then you look at differences in surprisals, and you figure out, are they sensitive to syntactic structures? And the overall upshot of this is that to a large extent, they are sensitive to some surprisingly complex formal structures in different languages. So here we have, this is an illustration from a sort of large scale study looking at a variety of different structures. We've also looked at some really subtle and complex formal structures in English. So like these are sentences involving what's called a filler gap dependency. That's what's involved in a sentence like, I know what the lion devoured at sunrise. There's a very interesting complex dependency that exists between the verb devoured there and the question word what. It's interesting because it actually sort of breaks the context-free structure of the English language. It's a very interesting kind of dependency. And so it turns out that when you look at these controlled comparisons, you can find evidence that language models, they not only understand the dependency, they understand many of the restrictions on when you can form that kind of dependency. This has even become a standard evaluation method for language models. So if you look at like the leaderboards on language models, one of the things you'll see is BLIMP. That is a data set of these minimal pairs of grammatical and minimally ungrammatical sentences where you look at the surprisal differences in order to figure out, has the model learned some kind of syntactic structure? And to a large extent, they have. Furthermore, what's really interesting here is that when you take this approach, you can actually get a quantitative theory, a quantitative picture of grammaticalness. So what I'm going to show here on the y-axis is the results of a human experiment where people were just shown a bunch of sentences and you ask them, is this grammatical, thumbs up, or is it ungrammatical, thumbs down? So people were not shown minimal pairs, they're just shown individual sentences. And what happens is that people don't always agree about what's grammatical. And so you have different rates of people accepting a sentence as grammatical. That'll be the y-axis, and the x-axis is going to be the magnitude of the surprisal difference that you measure from a language model, and you get a good quantitative fit. So like, for example, in the lower right quadrant there in the orange, those are cases where people are very, very unlikely to say something is grammatical. They think these sentences are almost certainly ungrammatical. And in those cases, the language model is proportionally even more sort of surprised by the structures in those sentences. So this actually gives you a quantitative match to grammaticality ratings, which you don't get if you're just thinking about grammaticality as a categorical thing. Furthermore, it's not just that the models have memorized what's going on here. We're often worried when we're evaluating language models that it's like if you see a language model do something impressive, there's often this worry that it's just regurgitating something back from its training data, right? And so you really want to make sure that it is generalizing from its training data and not just memorizing its training data. It turns out language models actually do learn to generalize using these grammatical structures. They don't just memorize. So you see that with sentences like this. So the arc here is a bit misplaced, but this is the same kind of sentence we saw earlier. So the keys to the cabinet sit on the shelf, the form of that verb sit. To figure out the correct form for that verb sit, you have to find the number of the subject. What's interesting is that in this kind of sentence, you can't just when you're trying to figure out the form of the verb, you can't just look back to the previous noun. The subject is actually kind of far away from the noun. It's been displaced. There's some stuff in between. This to the cabinet stuff is between the subject and the verb. And so you want to know, has the language model learned that you really need to look for the subject of a sentence in order to figure out the form of a verb? Or has it figured out use some kind of easier heuristic? One way you can figure this out is to actually train the model on an artificial corpus that has things like the keys are pretty, I lost the keys to the cabinet, the key is rusty. It's got lots of things involving these words. But in the training data, we've never actually separated the verb from the subject that it needs to agree with. So when you train on this filtered artificial corpus, you can then ask, would you then generalize to the actual human thing, which is that you need to look to the subject of the sentence and not just the previous noun. That would be evidence that these things can pick up on a structural generalization. And they can, when you train a language model on predicting text, predicting it to minimize surprisal incrementally in a text corpus, they very rapidly pick up on the human generalizations. This is accuracy evaluated using surprisal differences on test sentences like this. So very rapidly, they'll pick up on the structural generalization. Form of the verb should depend on the subject. What's really interesting, though, this is a very recent interesting paper. What's really interesting to me is that it actually seems to depend on the objective here. It depends on the function that you're minimizing. If you're trying to predict the probability of a token given previous tokens, you get the generalization. But if you set it up like this is a different way you could set up some kind of language modeling. You're actually not going to get it. So you could try to do a sequence transduction task where you take the sentence from a past tense form, like the keys to the cabinet sat, you bring it to the present tense, the keys to the cabinet sit, you'll still have to figure out the form of the verb. But when you train a transformer model to do sequence to sequence transduction, you do not get the structural generalization. Very interestingly, it looks like getting the right linguistic structure depends on training the model to do the right kind of incremental prediction. You have to be predicting the tokens given the previous tokens. You don't get it using other different objectives. And that's very interesting, and it points toward this idea that maybe this predictive distribution is kind of an important thing for understanding how human language works. So we've seen that neural language models can learn non-trivial generalizations about linguistic structure from data. I think what this means is that learning natural language syntax is not that hard. So it's true that these models take more data than humans do. So the GPT-2 model that I've been using was trained on 2 orders of magnitude more data than a human child gets, 1 order of magnitude more data than a human gets. So there's still a question of sample efficiency, of learning quickly from data. You see that actually in all neural learners. All neural network learners are slower than humans. But it looks like there's no conceptual problem with learning syntax. There was this idea in the 60s and 70s that the structure of language is just so complex, you could never infer it from data. The only way you could possibly learn it is if everything is basically built into the child learner. And I just don't see any evidence for that view anymore. It looks like more or less any powerful enough learner is going to pick up on this structure. So that's what language models learn. And now we're going to look at what they can actually tell us. We're going to start thinking about what language models tell us about how language works, in particular language processing. So this is getting at the information processing constraints of production and comprehension that language is operating under. So in language processing, we're thinking about production, how you take a meaning and produce an utterance, and comprehension, which is how you take in an utterance and then you decode it as a human. I'm going to be focusing almost entirely on comprehension in this talk. I'd be happy to talk about production in the discussion, although it's not part of my prepared talk. I think that's where the RLHF stuff comes back into play. But we're going to be thinking about comprehension today. And the interesting, important thing about language comprehension is that it appears to be in large part a process of incremental prediction. Same kind of thing we see in language models. So the human brain is a prediction engine. This is one of the major theories in neuroscience. One of the major functions of the brain is just predicting upcoming inputs. If I throw a ball to you, it's not so important that you know where the ball is. What's important is that you know where it will be so that you can catch it. So prediction is a major fundamental function in the brain, and language processing, human language processing, is no exception. You can see that in examples like this. So suppose I show you this scene. There's a boy and there's a cake and there's a ball and there's a whole bunch of stuff. This is an experiment, one of many experiments that shows how language processing in humans is predictive. Now, if you see the scene and I say to you, the boy will eat the, you're going to already look towards the cake there, because there's only one thing in this scene that the boy is likely to eat, right? So as soon as you can predict, based on the scene and based on your knowledge of language and based on your knowledge of the world, as soon as you can predict that I'm going to say cake, you're already looking towards the cake in this image before I say the word cake. That is indeed what we see when you make people sit and wear an eye tracker and look at images like this and listen to sentences. People look towards that word cake as soon as they can predict it, before the word is said. People bring all sources of information to bear to predict upcoming words simultaneously. So that's interesting. It looks like human language comprehension involves this kind of incremental prediction. But it turns out that the connection between human processing and incremental prediction as done by language models is even tighter than that. So we can use language models to get a good millisecond by millisecond picture of what's going on in language comprehension. In particular, the amount of information processing effort that it takes you to understand a sentence word by word is very well predicted quantitatively by the surprisal of the word under a language model. So the reading time per word appears to be a linear function of the surprisal of the word given its context as estimated using a sufficiently powerful language model. So how do we know this? So you can make people wear an eye tracker and then make them read a bunch of texts. And you get a cool time course like this. You can watch people's eye movements and you can figure out how long are people looking at a word before they move on to the next word. That's telling you how much processing are they doing on this word before they move on to the next thing. How much difficulty is there per word? And it turns out that is very well quantitatively predicted just by the language model surprisal, by the information content of the word as measured by a language model. So what we have here on the y-axis is reading times per word in a large corpus of text. After controlling for factors like the length of the word. And on the x-axis, we have language model probabilities as estimated from a multilingual language model. And then we have in the windows here, we have lots and lots of different languages. So we see across languages, you get a good quantitative model of reading time, a good linear model of reading time, just in terms of the language model surprisal. It looks like a fundamental thing that people are doing in language processing is just the same kind of incremental prediction that language models are doing. It's not a completely simple picture though, because recently language models have actually gotten better than humans at predicting upcoming words. So language models are actually kind of superhuman when it comes to predicting upcoming words. And I'll show you some examples here that show you that. I'm going to show you some examples of sentences that are easy and hard to understand. So here is a sentence that is easy to understand. The apartment was well decorated. And I'll give it a thumbs up. Perfectly easy to understand, right? And we have this kind of subject-verb dependency here like we saw earlier. Here's a second sentence. The apartment that the robot cleaned was well decorated. Still easy to understand, right? Maybe it's a little more complicated, but it's still basically comprehensible. And we see that now the dependencies are getting a bit more complicated. So if you want to understand what's going on with the verb was there, you have to look all the way back to the apartment there. And I've notated this as two, because it's like in this sentence, it's like I've embedded a sentence inside of another sentence, right? So we'd say this is embedding level 2. Now let's think about this sentence. The apartment that the robot who the service sent over cleaned was well decorated. So does this seem easy to understand? As people look at, yeah, people are kind of unsure. So I built it up piece by piece. But I bet if you encounter this sentence with no context in text, you would not. You would have to break out the paper and pencil, right? To understand what's going on here. So what's going on is that this is very, very hard to understand. The dependency structure is very complicated. There's lots of these long-term dependencies in the sentence. If you look at the reading times word by word for a sentence like this, the point where it starts to get hard is right here. It's when you start getting the sequence of verbs at the end of the sentence. So think about what's going on there. So you're at the apartment that the robot who the service sent over cleaned. You're trying to figure out who did what to whom. Right? And what's going on is that you have to think back to these words you heard a long time ago. They're all kind of similar to each other. You lose track of what's what. Essentially, your memory is somewhat limited here. And so it's hard for you to predict how the sentence should continue because you've gotten confused. You actually don't see this. If you just take a powerful language model like GPT-3, if you get the chat GPT probabilities or whatever, they actually show no particular difficulty for a sentence like this. And that's because they're better at predicting what's coming next than humans are. So for humans, you get really confused there. You can't predict what's coming next. For a language model, it just uses its many attention heads. It looks back at the nouns, and it's quite simple for it to predict what's coming next. It turns out, though, that language processing, the difficulty you experience in these sentences is still a function of this predictive distribution on words given previous words. You just have to make the models a bit less superhuman. So you can still predict the reading times per word using this surprisal, just with a bit of a modification. So here we have some human reading times on sentences that are complicated, like the ones that I showed you earlier, with different levels of embedding. So the red dots here, these are sentences like the report was surprising, very simple. The blue ones, these are these really complicated sentences like the report that the doctor who the patient liked annoyed the nurse was surprising. You have much higher reading times for these difficult sentences. And these are the reading times just on that end part was surprising. It turns out that the human data on this, it's not only a function of the grammatical structure and the dependency structure. So the difficulty that humans experience on sentences like this is also a function of the words involved. So if this kind of sentence is actually a little easier to understand, the fact that the doctor who the patient liked annoyed the nurse was surprising, people will read that faster. And if I say something like the fact was surprising, people will read that more slowly. So we can actually model this reading time data for these very complicated sentences by taking a language model and making a bit of a modification. Instead of now predicting a word given the previous words, you're going to predict the word given the previous words while minimizing the number of words that you use while making that prediction. This is sort of building in a bit of a working memory constraint into the model. And there's different ways to implement that constraint. When you do that, the language model surprisals very closely match the human data in both the qualitative and the quantitative patterns for these quite complex and subtle sentences. So we've seen that using this predictive distribution, using language models to capture linguistic probability distributions, we can model quantitative data about language, about grammaticality, about language processing. This is not only an extremely, what this shows is that this predictive distribution is just like a really useful thing to have if you're studying language. But I think it's actually deeper. I think this kind of predictive distribution is actually an important object to understand in order to understand human language, why it works, why it is the way it is. So we'll go into the last part of the talk. Now we're thinking about what do language models tell us about language? So language is a communication code. There's many different possible communication codes that exist in nature or in coding theory. Human languages are a particular subset of that. So human languages have properties that no other communication code that we know of has, and they also share properties with other communication codes. So the question is, what are the constraints that force natural language to be the way it is, not in some other way? Thinking functionally, this means that language is operating under the constraints that you have to be able to learn it, produce it, and comprehend it. And we've seen that processing, comprehension at least, is deeply entangled with incremental prediction. Human comprehension appears to be largely about incremental prediction. So if human language is shaped by information processing constraints, then human language should be structured in a way that supports incremental prediction. The same thing that's done by language models, and the same thing that appears to be done by humans in language comprehension. So human language is actually structured so that this kind of distribution is going to be, it's going to be easier to learn, easier to use than otherwise. And one consequence of this is that language should be structured so that units of language are predictable given local context. That's a general way that you can minimize the difficulty of incremental prediction. So things that are relevant for predicting a word should be relatively close to that word on average. We're going to see that that's true, and then we're going to see some evidence that language models succeed in part because they're also doing this kind of incremental prediction. So I'm going to look at three pieces of evidence that language is structured in a way that supports incremental prediction. The first is going to involve going back to these difficult sentences. So if we think about this horribly difficult thing with the 3 nested relative clauses and the very long dependencies, that's nearly incomprehensible. The nice thing about the English language is that the grammar of the English language does not force us into saying this. It gives us another way to express this meaning. You could just say the well-decorated apartment was cleaned by the robot that was sent over by the service. This is now the same meaning or close enough. It's easy to understand. The dependencies are short. You no longer have these long-term correlations dependencies in the text. And it turns out it's actually a general property of languages that their grammars are configured in a way such that the relevant words are usually on average close to each other. Here's one way we can see that. So it turns out this is a sort of statistical universal of human languages, that relevant words are close to each other. And here's a corpus study demonstrating that. You can take a large body of text, naturally occurring English text, and grab a sentence from it like this. Here's a sentence. This story comes from the AP. And you can annotate it in terms of the grammatical dependencies and the lengths of those grammatical dependencies. So the from to the AP dependency there is of length 2. You can get the total dependency length for the sentence. And you can plot that in a space like this. So this is a sentence with 6 words and the total dependency length is 6. It goes here. And you can get the average dependency length per sentence length for the whole English language in a corpus. This is a statistical signature of how far words are away from the relevant words for predicting those words. And then we can ask, is the English language configured in a way such that relevant words are close to each other, such that this curve is lower than it would be? To do that, we would want to compare the English language, the English corpus here, to various other ways that the English language could be. So we can imagine other systems of grammar rules for the English language, other context-free grammars for English, and then we can imagine what would all the utterances in the corpus look like under those grammar rules. So these are like random reorderings of that original sentence under different possible context-free grammar rules for the English language. Each of those reorderings has a number. These numbers are telling you what would the dependency length be like in English under other random rules. You can plot them in the same space, get the average, and what you find is that the actual English language has shorter dependencies than you would expect from chains. You can keep playing this game. You can come up with lots of different baselines. These baselines would represent different, hypotheses for what the structure of the English language could look like. And what you find consistently is that the actual English language is set up in a way such that the relevant words are close to each other. Black lines below all of the colorful baseline lines. And it's not only English, you also find this in 54 different languages of the world. So this appears to be a statistical universal language. Words that are in dependencies, in these grammatical dependencies, on average tend to be close to each other. The extent of the effect varies from language to language, but all of the languages show this effect of dependency length minimization. And this is not just a statistical thing. This idea of minimizing lengths of dependencies actually underlies a lot of the correlations among word orders that linguists have been studying for the last century or so in the field of typology. You can actually predict the properties of languages using this idea of minimizing lengths of dependencies. And it's even been claimed that this idea will explain why languages are usually context-free or mildly context-sensitive in terms of their formal complexity. So this is an example of how language is set up in a way that maximizes local predictability. The relevant things for predicting a word are usually close to that word. Here's another example. If I show you this thing, and I ask, where are the cute kittens? 10 or 5. If I show you this thing, you're probably going to say the kittens are in the big brown box. You're probably not going to say that they're in the brown big box, right? So that second order for the adjectives, it sounds a little bit weird and bad, right? It sounds either like it's wrong, or it sounds like it's expressing some kind of other meaning, right? Like maybe a big box is a special kind of box. So the first order is basically a thumbs up, and the second order is basically a thumbs down. And this order of adjectives, these preferences for adjective order are actually, they show up in many different languages. So it's not only an English thing. There's a particular order that adjectives like to go in when you have multiple adjectives that are modifying it. And this comes from maximizing local predictability, making it easy to do incremental prediction. How can we tell that? Well, each adjective is going to have some value in terms of predicting the noun, in terms of making the noun predictable. You can quantify that using this measure called pointwise mutual information, which is just the surprisal difference between the noun given the adjectives and the surprisal of the noun. You can estimate that using a language model. So that's a number that's telling you how well does this adjective predict the noun. And when you apply that to adjectives, you find that the adjectives that tend to go close to the noun are the ones that have higher pointwise mutual information. The adjectives that go farther away tend to be the ones with lower pointwise mutual information. This actually can provide you with an explanation for why we order the adjectives in the way we do. And the bolded study here is a corpus study from 32 different languages, where we showed that consistently across all of the languages, the pointwise mutual information predicts the order of the adjectives. So it looks like adjectives are ordered so that the most predictively useful adjectives are close to the noun. I think this idea of maximizing local predictability goes even deeper, though. So if I ask you to describe this thing, you're probably going to say it's like a cat and a dog, right? Or it's a cat with a dog. And when you say something like that, there's this nice systematic homomorphism between the structure of the meaning and the structure of the form of the utterance you're producing. So part of the utterance corresponds to the cat, part of it corresponds to a dog. This is the basic principle of compositionality that underlies a lot of what makes human language distinctive. So what's not often remarked on, though, is that you could have other systems that are still systematic in the way that language is here, but different. So the interesting thing about language is that we take the words for something like a cat and a dog, and we just concatenate them together. There's a part of each of the sentence corresponding to each part of the meaning, and we just concatenate them together. You could imagine a communication code that would be systematic, but it would look like this. So you'd say this thing is the way tagtahogged. So you would take the word for a cat, you'd take the word for a dog, and you'd interleave them together. And yet human language is not like this. Human language is not like this. Think about how terrible this would be from the perspective of local predictability. So now the information about a cat is spread out through the entire form, through the entire signal. The information about a dog is spread out through the entire signal. In the actual human-like thing, a cat and a dog, the information is contained and concatenated together. The information is contained within phrases that are local to each other. And if this just seems, it might seem like it's just crazy to think that a communication code could work like this. You might think, oh, well, obviously you concatenate the words together. But actually, this kind of code, it would be excellent if you were trying to come up with an optimal code for communication in the presence of extreme levels of noise. So in communication theory, you often study things like, how would you come up with a code that enables you to transmit messages through deep space where you're losing almost all your information? In that case, you actually want to spread out the information as much as possible throughout the entire signal. That's sort of the underlying idea for things like Hadamard codes. And that's not what we do in language. In language, we're less concerned with getting through a huge amount of noise, and we're more concerned with local predictability. So if I say a cat and a dog, we have good local predictability. So we've seen some ways that language is structured in a way that supports local predictability. And now the last thing I'm going to show you is some evidence that language models are going to succeed in part because they're also doing this kind of incremental prediction. Exactly the thing that natural language appears to be set up to support. So this work is somewhat responding to a perspective that's recently been put forward in the field. So this is an interesting letter to Nature, and it's not only them, but other people have had this idea. There's a claim that large language models can produce impossible languages, not generated by principles governing all known human language, just as well as, if not better than natural language output, and cannot distinguish between them. So there's this idea in the field that, language models don't tell us anything about language. The reason they don't tell us anything about language is because they could learn just arbitrary sequences of symbols just as well as they can learn language. So it doesn't matter whether you have linguistic structure or not. These things are just generic sequence models. And what we're going to see in these studies is that that's actually false. Languages are actually harder for language models, for neural language models, transformers in particular, to learn when their linguistic structure is disrupted. When you disrupt linguistic structure, you actually end up with something which is harder to learn for neural language models. So we demonstrated that in a series of experiments where we trained a GPT-2 architecture on corpora of English and corpora of English where we have perturbed and destroyed the linguistic structure of the language in various ways. So the first result is what we get from not shuffling, not perturbing the structure of the training corpus at all. So you just train on normal English text. You have sentences like he cleans his very messy bookshelf, which gets tokenized like this. And as you train, you get a loss curve that looks like this. So you very quickly minimize surprisal and learn a good model that can predict the upcoming words. The next thing we did is what we call non-deterministic shuffle. So here we disrupted the linguistic structure in the training data by just taking each sentence and randomly shuffling the words in it. So that destroys all the information in the order of the words. And it destroys, for example, the well-nested context-free structure of the language. It produces just a sort of bag of words. And when we do that, we find that the language model cannot learn from that shuffled corpus as well as it can learn from the original. This is maybe not so surprising though. So think about it. We actually injected randomness into the training data when we did this shuffling. And that means that the language is actually now inherently harder to predict than it was before we shuffled it. So there's actually no way the language model could actually ever be as good at predicting this stuff as it is at predicting the real language. The next case is more interesting though. We apply a deterministic shuffling function to each sentence. So we have a random permutation function, and we apply that same permutation function to each sentence consistently. This is going to have the effect of totally destroying the structure, the context-free, well-nested structure of the sentences, but it's still deterministic. So we haven't injected any randomness into the training data. In principle, in terms of global predictability, you should be able to learn to predict these sequences just as well as the original sequences of language. And yet you can't. When you train the language model in the deterministic shuffles, they don't do so well. And that's because I think you've taken the words that are relevant for predicting a word and you've moved them really far away through the shuffling procedure. If you then shuffle things in a local way, going through with a small window and applying the same deterministic shuffling, this is still going to destroy the hierarchical structure to the language, but it's not going to move things as far away. Then you still get that you cannot learn these things as well as actual natural language, but you still do better than the full global shuffling. So why do you do badly on those languages that have been shuffled? I think it's because linguistic structure is set up in a way that supports local prediction. When you destroy the linguistic structure, you destroy the ability to do this local prediction. And so your incremental prediction is consequently harder. So language models struggle to learn language when you disrupt the local predictive structure. What do we make of this? Concluding now. We've seen that using language models to capture linguistic probability distributions, we can model quantitative data about language, about grammaticality, about processing. We've seen that the information processing constraints, which are to some extent shared between humans and language models, can actually explain properties of language, because human language processing appears to be about this same kind of incremental prediction that language models are doing. So going back to the functional perspective on language, we've thought about language as operating under constraints, information processing constraints, especially on comprehension. Those constraints appear to be wrapped up in this predictive distribution, this task of incrementally predicting a token given previous tokens. This approach creates an interdisciplinary nexus where we have linguistics, which tells us what language is like. We have cognitive science, which tells us what human thought is like, and machine learning, which gives us these language models. And now all these fields can communicate with each other through this information-theoretic lens on language. So thanks for your attention, and thanks to my many great collaborators.
Ronnie, you're on.
Hi. So yeah, so hi everyone. And I'm Ronnie Katsir. I'm from Tel Aviv University. Can people hear me over there in the room?
Yes.
Okay, great. So I'm the designated discussant for Richard's talk. And Richard is, can I share some slides? Is that okay?
Go for it.
Okay, great. So wait. And I believe I have something like 10 minutes now.
Approximately.
Okay, very good. So let me just share the slides. Okay. So I'm going to talk very briefly about a couple of things that Richard talked about in his very interesting talk. And I'm going to focus on one thing, just one point out of the many many different topics. So first of all, a quick point about something that Richard was talking about early on about the ability of large language models to capture the grammatical structure of language. So, in the work that we heard about now, we heard about all kinds of filler gap dependencies and the ability of large language models to do well on all kinds of minimal pairs there. In more recent work that Nulan, Emmanuel Shemla, and I did, we looked at this a bit more closely and checked some other filler gap dependencies, just basically simple extensions of the very basic ones. And what we saw is that the large language models actually fail completely to learn those patterns. So the Wilcox, Futrell, and Levy paper looks at all kinds of different islands, among other things. And we looked at something that that is sometimes referred to as a cross-the-board movement, which is basically that when you have a gap in one conjunct, you should have a gap in the other conjunct as well. So 1A is not good because it has a gap just in one conjunct. I know who John met recently, gap between met and recently, and is going to annoy you soon. No gap in the second conjunct. And the good 1B, I know who John met recently and is going to annoy soon. And which is okay, gap in both conjuncts. The large language models that we looked at, and we looked at a whole bunch of them trained on different corpora, some of them much bigger than anything that a child can see, and all of them are more surprised by the grammatical continuation than by the ungrammatical one. So it's not just so if a model learns the pattern, it should assign a much higher probability to the correct continuation. The ungrammatical one is not a common error. It should be much less likely. But instead, the models assign an actually higher probability to the ungrammatical continuation. And this is just with one example, but we varied the choices in all kinds of different ways. And all the models, except for GPT-3, got terrible results. They failed almost all of the time, and so it just so happens, and this is of course an empirical finding. It could have been otherwise, but it just so happens that these models do not learn what any child knows, even after exposure to hundreds and thousands of years of linguistic evidence. We also much more tentatively checked what happens when we artificially enrich the training corpora, and at least one model, the one that we were able to work with in this way, improved quite a bit, which suggests that when the models fail, it's not just because the models themselves are very bad, even though I'll say a word about that in a moment. I think these models really are much less good at learning grammar than one might expect, but that the data are not rich enough, and that we are in some sense prepared to know these things in a way that a neutral model is not. But that's more tentative. I think what's not tentative is that these models really show us no evidence of learning the relevant grammatical pattern. Now, in other work, we looked at what makes models succeed or fail. I'll be talking about that more on Wednesday, so I won't elaborate on that now. I'll just mention that the standard training techniques for neural networks, and these are the techniques that have been around for many decades now, prevent them from succeeding not just on the incredibly complex syntax of natural language, they prevent them from learning things like A to the N, B to the N, the simplest formal languages. So standard training basically guarantees that these models will fail. We changed the training technique and used instead a principle of economy, which is kind of a very standard and well-known principle of minimum description length, very close to Bayesian inference. And when we did that, the models did manage to learn the patterns. I'll say more about that on Wednesday. So the models that we have simply fail on the simplest languages there are, and they certainly don't manage to learn natural languages. So that's one thing. But I think the most, to me as a linguist, the most interesting part of Richard's talk had to do with explaining things. And I think that's a really important endeavor. And the proposals themselves, there were several, were really interesting. And just a tiny bit of general context for this. So when we're doing, so it's of course very different when we're doing engineering and trying to build good models for all kinds of purposes. But when we're doing empirical science and trying to understand how the world is, then the only way in which we can make progress is by inference to the best explanation, sometimes referred to as abduction, also can be framed in terms of Bayesian inference. And we try to explain. We don't try to approximate surface frequencies. We try to understand the mechanism. We try to understand how things are. And how things are can be something that is obscured on the surface, but is the best explanation. Laws are those parts that are kind of the major components of best explanations. And it's about that. It's about the best explanation and not about fitting the data or matching surface probabilities. And I think the goal of explaining, which Richard was talking about, I think that's the goal in that is the shared goal of cognitive scientists, linguists, other people working on language as it is in our heads. And of course, when we look at the different languages of the world and try to figure out what the best explanation is or reason about best explanations, we need to deal with the fact that there are lots of different interacting factors. So there are the representations themselves. We're born with something, and people can argue and have been arguing and should argue about what we have in terms of our ability to represent things. We can think of it as an innate programming language that we're born with, and it can be Python, or it can be, which would be a bad hypothesis, but it could be Python, it could be a programming language where we write context-free grammars, it can be the weights in an LLM, it can be all kinds of things, representations. It's the learning mechanism, another factor that interacts directly with the representations, communication considerations, processing, and so on. And in one of the papers that Richard mentioned, he proposed that minimizing excess entropy is part of the explanation, the Futrell and Hahn, the recent paper, which is a very interesting idea. And I think it invites kind of thinking about all kinds of things that linguists talk about. And here are some very, very basic things that linguists have talked about in the past and still think about. One is constituency, which was hinted at. And the fact that linguistic are linguistic knowledge makes reference to something like bracketing, like parentheses. And there are different ways to talk about it, but that's the general idea. And lots of things in language are sensitive to that. So when we put something in the beginning of the sentence, as in 2a, talk to Kim, John will, that's something that's well bracketed, that respects the bracketing of John will talk to Kim. Again, different ways to cash this out and so on. If we try to put something in the beginning of the sentence that doesn't correspond to that, like talk to John will Kim, that's not okay. Okay, now, I don't know if something like minimizing excess entropy can explain that. I think it's interesting. I think the paper itself hints at some things in this direction. I think it might work. I don't know. It strikes me as not entirely trivial because talk to are these two elements are very well correlated, whereas to Kim much less so. So I'm not sure this will work out, but I think it'll be interesting to check that. Other things that would be interesting to look at are things like the fact that our meaning representations are such that they make reference to entailment, and there are reasons to think that. And another thing is that there is some kind of separation of structure in syntax and meaning in semantics with a very tight border. So semantics makes reference to syntax, and there are arguments for that, but the syntax seems almost entirely blind to our knowledge of things. And can this be motivated in terms of excess entropy or something like that? Perhaps, I don't know. I think it would be interesting to look at. I had some immediate questions about this proposal. One is what I just mentioned about talk to, which two elements that are tightly correlated, whereas other things are less tightly correlated, but do move together. And so the first question would be whether minimizing excess entropy makes the right cut in this case. The other thing, kind of more broadly, is why this particular criterion, and I know that there were other proposals, information-theoretic and otherwise, there, but which of these is or are the correct proposals? And I think more crucially, how do they fit into an explanation exactly? So do they factor into processing, into learning? Do they shape the evolution, the biological evolution that gives us the programming language that we have? There are all kinds of different possibilities, and I think those are things that would be very interesting for me, for many people, I think, to understand. And what is it that we explain here exactly? Because if we're explaining what speakers do in terms of their inference, that's one thing. If we're explaining, as I mentioned a moment ago, how evolution shaped things, that's a completely different project. And one can imagine information-theoretic considerations entering into both, but in very different ways. So I think those were... and then, of course, there are lots and lots and lots of different things that linguists have looked at, cross-linguistic patterns, that, at least to me, seem to invite very different kinds of explanations, not the kinds that have to do with information theory or locality, like the one that I mentioned earlier about if you have a gap in one conjunct, you have a gap in both, or the fact that you can't ask a how question about a relative clause, which is universal across languages, or the fact that you cannot have a determiner, like a quantifier, glebe, an imaginary thing like every and some, that means more or less what the verb outnumber means. It's a very normal meaning to have, and the verb outnumber has it. But to our knowledge, there is no language where there is such a quantifier. Glebe boys smoke, meaning there are more boys than smokers. Lots and lots of other things that linguists care about and that linguists use routinely in order to reason about the inference to make inferences to best explanations. And of course, these should be part of the discussion when we talk about explaining natural language. These are things that have been out there, and I'll stop here.
Okay, thank you very much. Richard will get a chance. Now, this is because Richard started late, so we're gonna make a few exceptions here. Richard gets to answer Ronnie now. But remember, you're gonna be speaking several times in this talk and so in this series, and so will Ronnie, and it won't all be settled in this session.
Yeah.
And then it'll be opened up to the general audience for some questions, and I'll even give you the written questions just so that you can see whether there's any you would like to favor.
Okay, well,
Okay, but go ahead.
thanks. Yeah, so thanks for the commentary. I have a few thoughts. So just for those listening, so the commentary is talking about this excess entropy theory. That's in one of the papers that I linked on my abstract. But that theory is basically just a formalization of this idea of maximizing local predictability that I was talking about in the talk. I didn't call it excess entropy in the talk, but minimizing excess entropy is the same as making things easy to predict incrementally. And there's a particular information theoretic formalism that goes along with that. Yeah, so that particular formalization is relatively new. And I see all these examples that you've given as sort of challenges to see if the theory can meet. And for most of them, I don't know yet. I have thoughts for many of them. I will point out that for a lot of these semantic universals, like involving glebe and XOR. So XOR, this is this question of why it is that all human languages are based around logical connectives like and or, and never around weird stuff like XOR and NAND that you study in a logic class. So why would that be the case? There are efficiency-based theories that have been put forward for the existence of monotonic quantifiers and for the logical connectives we use. I'm thinking of stuff by Nathaniel Imel and Shane Steiner-Threlkeld, where they're thinking about systems that are maximizing information transfer while minimizing complexity, where complexity is defined as learnability by a linear classifier. And there's similar explanations for XOR and NAND that are out there. I'm thinking of a paper by Engehard. So it's not, I think that explanations in terms of information processing are available for things like this. But of course, this is to be done. And this is the world we live in. I see this as the work for the coming decades of language science, is addressing like how do these very particular formal properties of language come out of information processing, or maybe they don't. Another point was about the like the goals of the science of language, finding explanations. I'm in strong agreement that we should be looking for explanations and not just matches to surface data. But I think that looking for good quantitative matches to surface data can be an excellent way to come up with new kinds of explanations. So an interesting example in the history of science is we all know this story about how we moved from thinking about the world as having, the universe as having the world, the earth in the center of it, to thinking about the universe as having the sun in the center of it. This debate between like Galileo and Copernicus and these guys. And so there was a Ptolemaic system for understanding how the solar system works, where the earth was at the center. It was really complicated to get the right predictions, the right quantitative predictions out of that. You had to add all these epicycles to the system. Copernicus came around and he proposed that you should have the sun at the center. And his system was just as complicated. You might hear some people say that Copernicus' system was simpler. It wasn't. It was just as complicated. The real hero of that story was Kepler, who was looking at massive amounts of new empirical data on star positions that was collected by his advisor. And through essentially decades of just pure curve fitting, he discovered elliptical orbits. He had to throw away the idea that the planets have to go in circular motions. That was arrived at purely by looking for a good quantitative fit to the data. And that was the real revolution in astronomy that eventually led to gravity. So I think that it's true that matching quantitative data is not always the best way to go, but often it is. Often trying to match the quantitative data can give you a new theory, gives you a way that it'll lead you to abandoning previous ideas about how the world has to be. I think that taking a quantitative approach to language science might cause something similar in the science of language, might cause a revolution in how we think about the underlying formal structures, abandoning our old ideas of simplicity. So one interesting idea in linguistics is you might have heard of universal grammar. It's the idea that there's like a sort of universal formalism that we all have in our heads for understanding language. I think this approach is interesting, but I think it cannot. So it's the idea that you were essentially born knowing that language is going to be a certain kind of context-free grammar, and then you just sort of fill in the blanks based on data you have. I think this is interesting, but I think that kind of approach actually can't give you the deepest possible explanation for the form of language. Just saying that humans have a certain programming language in their head, a certain universal grammar, that doesn't give you the deepest explanations because it leaves you the question of why that programming language, why that universal grammar, why is universal grammar one way as opposed to some other way? I think the deepest explanations are going to come from the inherent information processing constraints that humans have as the result simply of being organisms, being intelligent organisms. And so I think this sort of processing efficiency stuff provides ultimately the deepest explanation. The last point of response is this is probably not the place to get into the back and forth about like the surprisal ratings on these complex sentences. But I'll point out that the failures that were shown on that slide, those were for minimal pairs that did not match the words for which the surprisal was compared. So the paper that was referenced, it also includes surprisal differences based on controlled materials where you have the same words that you're comparing, the most controlled comparisons. And on those, the GPT-2 architecture actually does get above chance performance for the across the board movement that was shown there. And so that's just a taste of the kind of back and forth you'll see if you dig into the targeted syntactic evaluation literature. That's it. Thanks for the commentary. It's very interesting. And let's be in touch also. So let's open it up. So we do it.
Say out loud, Jenny Valiant, what has a
Jenny Valiant has a question.
Jenny Valiant should turn herself on.
Okay, are you going to decide who gets to go, or do
You
there's a question from the room?
Yes, you can take the question from the room now.
Okay.
I just have a quick question.
Yeah.
In the shuffling slide.
Yeah.
You broke up bookshelf into
Yeah,
three,
yeah.
and specifically you chose to leave the S with books.
Yeah. So we're shuffling at the token level. So the shuffle there is actually random. It's just you just fix the random seed for Python.shuffle, and yeah.
But if you are studying syntax, why not keep the symbol elements together? That's
Oh, so the point of those shuffles was to disrupt syntactic structure.
But you're also disrupting semantics that way, because you're breaking a word in three and also not according to book and shelf.
I don't know. Yeah, okay, so the question was in the shuffling examples, we were disrupting syntax by moving the plural marker away from the word it belonged to. But in the same case, we're also disrupting semantics. So that's the point. Is that correct? So I don't know that we're disrupting the semantics because we're applying a deterministic transformation. So like an uber powerful decoder should be able to get out exactly all the information from that scrambled sentence as from the original sentence. So maybe the semantic structure has been disrupted in terms of what parts are local to what other parts. But I think in terms of just information content of the utterance, we actually have not disrupted. We haven't disrupted it in those.
Okay, the next question is from Ginny. Are you there?
Yes, I am. Hi, and can you hear me?
Yes.
Great. So thank you for all of these challenges in your work to people who come from a more linguistics background. My question is, given your argument about the structure of language being dependent on maximizing local predictability, why do multiply center embedded sentences exist at all?
It's a very good question. Very good question. So the first thing to note is they do exist. They're very, very rare. So there's a very widely cited corpus study from Carlson, who finds that in written language, these three-level embedded sentences, like I showed you, essentially don't happen. They're vanishingly rare in text. Nevertheless, there's a question of why they happen at all. And I think, so in terms of local predictability, you have to think about everything in the sentence. And yeah, it's people will use an alternative structure if they can, but by having sentences nested within sentences, you're maintaining the local predictability relations within those sentences. And so I think that if you really think through what local predictability is going to predict there, it's not necessarily going to say that you're never going to have center embeddings. It's just that they're going to be rare. And you're only going to be forced into having a center embedding like that if otherwise you would be disrupting the internal sentence structure of the sentences too much. I know that's kind of hand-wavy.
Yeah,
That's what I have. That's what I think of on the fly right now. Yeah. But yeah,
Okay.
good question. Very good question.
thanks.
Okay,
Now, so what's next?
Steve Hansen, you're on. Up to be.
Oh, can I see the questions here?
Yes, in fact, I'll let you do it on mine.
Yeah, that would be
Then you
easy.
can answer them orally. Just a second. Q&A. All yours.
Great. Okay, who's up next?
Well, I'm waiting for Steve Hansen, who's been elevated, but he doesn't seem to have heard it.
I
So-
seem to be, my video's off, Stephen, you've turned it off.
I can't turn on your video, but I turned it
Okay.
on.
That's fine. Hi, I very much enjoyed your talk. I thought that the empirical details were great. One of the things that caught my attention and concerned me was you said you computed the bits of a sentence using GPT-2.
Yep.
In what, I probably should go read your paper, but how did you do that exactly?
Oh, yeah, that's a very good question. So, simple, so these language models just are probability distributions. And so nowadays you actually.
Well, that's certainly one aspect of it, but I would call them dynamical systems.
Uh-huh.
That use probability distributions, but yes, sorry.
Yeah, well,
Just-
one of the things they output though, it's actually hard to get the real probabilities out of like ChatGPT now. They changed the API.
Yeah.
But the older models like GPT-2, you can just run it on your laptop and get the probability of any string. And that's the probability that would have generated that string.
Within the context of that population of training data.
Yeah, it's the probability based on its own training data. So I mean, one like little subtle thing is that GPT-2, if you really want to get into the technical details, GPT-2 will not give you a probability for the first word, only for the rest of the words. And so to get those probabilities, I actually gave it a context which was just text : and then those sentences. Yeah. But getting a probability out of a language model, this is the basic thing they do. And so if you have it running on your computer, you can just get the numbers.
I see. I guess the complaint might be that the GPTs in general aren't necessarily constructing the entire probability distribution of human language or the potential of human language. Therefore, your sample has some error bias built into it. And anyway, it's a very nice, the fact that there's linear relationships here that turn out between the surprises is quite amazing. The other thing I'd like to say just in passing is A to the N, B to the N. Actually, this reminds me of something from the 80s and 90s in connectionists, since I actually come from that era. Yeah, of course, the large RNNs were doing very large finite state regular grammars, but there's also many examples of context-free grammars. And then when Schmidt-Huber came by with LSTMs and other, so there's a lot of, flotsam and jetsam out there that we can use to produce some kind of grammar estimate. Not infinite in any sense. But that's actually, I think, an old reference.
Oh yeah, so the early connectionist work on grammar learning is fascinating. Yeah, and it's quite relevant to the modern stuff. I think more connections should be made.
Okay, you want to scroll through your questions?
Yeah, there's questions. And also Ronnie has probably.
Oh, okay, Ronnie can.
Yeah, let's do it. Yeah, Ronnie.
Ronnie's.
Okay, so just a couple of quick things. For the A to the N, B to the N, I think, yes, the old work that looked at those formal languages was important and should be, I think, more central to current discussions. I think it really is striking that current models simply fail to learn these things. So they're incapable of learning the correct grammar, even for these simplest cases. And it's the the objective function, because representationally they're capable of representing this knowledge, but the objective function or any version of cross entropy plus simple regularization guides the training to a wrong place in the space. And I think that's striking. And if these models cannot learn even these very, very, very simple patterns, then I think we all need to think a bit about what we're doing with these models. Those should be the easy cases.
You're talking about you're talking about transformer model architectures.
All of them, LSTMs, simple recurrent neural networks.
Well, there is some work. We published something back in 96, showing fairly generalizable grammar learning. I'm not going to go into that right now, but I know of a lot of examples of this for lots of people. Back in this time period, we did a lot of these kinds of grammar learning. They work just fine.
Now, Richard's going to look at some of the questions. Okay, Ronnie, did you have something else?
Yes. So the other thing, so for learning, I'm talking about perfect learning, not about approximating for a few hundreds of cases. I'm talking about true for all n. And we can.
And hardly perfectly learn anything, really.
No, it's not true. I think humans do learn perfectly, but we can talk about that separately.
Yes, let's suspend that one. We can take it.
The other.
I'll hold it a sec, just a sec. We're going to take questions from the attendees.
Okay. So should I read them?
Well, the ones that you want to answer.
Okay.
Skip the tribute.
It says there's 12, but I only see 3. Oh, here we go. Here's a question. LLM from David Lizotto. LLMs and the way you approach them today, showing that they can learn local predictive structure from large amounts of data, do add an argument in favor of the innate ability of humans and Chomsky's poverty of the stimulus, since humans learn these structures of language with much less data. So this is getting at this poverty of the stimulus question. The question is, how does this deal with this question of poverty of the stimulus? I've talked about this a little bit. I think, so the question is, how do the results here bear on the idea that humans have innate sort of instincts toward learning things like language? I think there's 2 ways to think about it. One way to think about it is that this is, the language model performance is evidence that general learners can pick up on the structure in principle. It's true that they take 10 or 100 times as much data as humans do, but it's also true that humans have lots and lots of other input from multimodal input, rich sources of information. And it's also true that humans are generally slower than neural models at learning basically anything. And so I think the results that I've presented are perfectly consistent with the idea that more powerful domain general learners are going to be able to pick up on this structure faster. I basically don't see any particular reason to think that domain-specific linguistic knowledge is going to get us to faster learning as opposed to domain general, just general, more sample efficient learners. Another way to think about it, though, is you could imagine that humans actually have a bias towards, maybe what humans have is an innate bias towards languages that have this kind of local predictability that we see from language models. People might have a bias towards learning the kinds of languages that are going to be easy for them to process. So it's possible that that is actually innate, but I think what that points to is that the innate knowledge is not the deepest explanation for why language is the way it is. So well, you could ask, why do humans have this innate knowledge? And it's because that innate knowledge points them towards languages that are going to be easy for them to process in terms of their inherent information processing limitations. Yeah, question in the back.
Next question would be,
Oh, sorry. Okay, okay. Let's see.
One last question.
Yeah, um. Okay, here's a small technical one. Oh, here's a good one. So there's a question from Jan Hukinen. So in German, they're all good questions, but this is also good. In German, the main verb comes at the end of the sentence. Is this the exception of locality? So I often get this when I present that dependency length minimization result. There's always some German in the audience that says, but we put all the verbs at the end of the sentence and the dependencies are very long. In fact, they are. They are long in German. But in that plot I showed you of all the different languages, even German has shorter dependencies than you would expect under random grammars for the same sentences. So German is one of the languages where there appears to be a weaker minimization of the dependency length, but it is there. It's there in all the languages we tested.
Yeah, I'm sorry to have to be draconian now, but
Yeah.
we went on longer.
All right,
I'm gonna ask Simon to cut the recording, but what I want to the rest of you, I suggest you don't lose your place in the line. We're gonna have a break and then we're gonna come back. Stay on even when it's in silent mode.
And I'm happy to discuss all this stuff offline. I'll be around today and a bit tomorrow.